Okay, so today I want to talk to you about the factors affecting acidity. The first factor I'm going to talk to you about is the inductive effect. Now, the inductive effect is caused when you have an electron withdrawing group or an electronegative element, and it attracts electron density towards itself in a bond. Now, when we remove a hydrogen, an anion is formed, so the more of the electron density we can pull away, the more stabilized the species is. So in these compounds below, these are more acidic than if the substituent was switched for hydrogen, as they can attract electron density towards themselves. Fluorine is more electronegative than chlorine, so this will be more acidic, and the most acidic species on the slide will be the one on the far right, which has two chlorines and two electron withdrawing effects. So we can extend this principle to carbons, and the alkyl groups actually donate electrons. So if we have a look at if we're removing the hydrogen from the primary, you've only got one donating effect there, two on the secondary, and three on the tertiary. Obviously, donating electrons is not going to stabilize an anion, and so we get the effect where the primary is the most acidic and the tertiary is the least acidic. Hybridization. Now, there's many ways to think about this, but how I like to think about it is that the s orbital is lower in energy than the p orbital, so it's going to be easier to remove a hydrogen from this orbital. Therefore, we get the most acidic species being the sp, and they're a lot more acidic than sp3. Now, probably the main effect we have is the mesomeric effect. So the more we can delocalize a charge, such as the anion, the more we stabilize it. So here, if we have a base and we remove that hydrogen, obviously you can put the negative charge onto the carbon, but we also have a resonance effect where you can delocalize it onto the oxygen. And similarly with the alkene, we can resonate the negative charge onto a different carbon. And this just shares the electron density out between the carbon and oxygen, or the two carbons, stabilizing your anion, making the species more acidic. Okay, hydrogen bonding. This is quite obscure and one which isn't really a main factor. But here we've got two different alkenes, the cis and the trans. So although they look the same, they have differing acidity. So if we remove proton, we're going to have no hydrogen bonding in the trans alkene, whereas hydrogen bonding exists in the cis alkene, and this stabilizes the whole species. So we find that the cis alkene is slightly more acidic than the trans. Solvent effects. Now obviously this won't affect different species, as they'll all be in the same solvent, but I thought it was good just to cover it. So when we have a Bronsted acid, this is the equilibrium you will form. And so the more we can stabilize the ionic compounds, the more acidic our species will seem to be. And to stabilize these ionic compounds, we need a polar solvent, and hopefully one which is protic, which will be able to hydrogen bond and shift the equilibrium to the right. So we're looking at water or ethanol, be it making species seem more acidic than if we say put them in benzene or BF3. Carboxylic acids. Now this is an example that I like to bring up quite a lot. So obviously both in all carboxylic acids you have a resonance effect, but here it's not the resonance effect which is important. The benzene ring has a delocalization of electrons, and this allows the electron density when you form the anion. It spreads out all over the ring, and so this makes the benzoic acid a lot more acidic than your regular carboxylic acid. Just another point to touch on benzoic acids. We're not talking about the mesomeric effects here, but inductive effects. So if you place an electron withdrawing group, you're going to increase acidity, because obviously that negative charge is then delocalized more, and you've got the electron withdrawing group pulling the electron density and kind of reducing the charge, which makes it more acidic. And with the electron donating group, you reduce the acidity because there's already a large delta negative on the ring.